In this course, we'll often want to write classes that can store any data type, not just containers of ints or containers of strings, but containers that can store any type you might think of. Such data structures are called ADTs, abstract data types. In C++, we can write abstract data types and also functions using a feature called templates. Let's look at some examples where templates could be useful. Suppose that, for some reason, you wanted to write a function to add two values together. The most obvious implementation of such a function might look like this. So far, so good. Now, your team starts using the add function all over the codebase and grows to appreciate the elegance of the abstraction. However, folks working on other parts of the codebase that deal with floating point values might now grow envious of this elegant simplicity. They are still stuck in the dark ages of writing x plus y themselves. To accommodate their requests, you implement another such utility function. You see where this is going. The next thing you know, you're spending all of your working hours writing and testing overloaded implementations of the add function. All of these overloaded functions are identical except for their types. Wouldn't it be nice if we didn't have to write out all of these overloads? If we go even further, imagine that someone asks you to write a version of the add function that takes an object of class bank account, but that you don't have access to that class's definition. How can we write a function that uses an unknown type? C++ templates are a mechanism for specifying what a function or a class ought to look like without knowing everything about that function or class. A template is a pattern that the compiler can use to instantiate instances of a function or a class. Templates are most commonly used to write many versions of the same function or class that can work with different types. In our example of the add function, we can write one template and then let the compiler instantiate all of the actual functions. Here, we have specified, using the keyword typename, that t is the name of a type that can be substituted in when the compiler instantiates one of the overloaded add functions. So, when we try to add two integers together, the compiler will automatically generate an add function for us with t set to int, giving us a function with the signature int add, int x, int y. If we try to add two doubles together, we'll automatically get a function called double add, double x, double y. If we try to add two matrices or two bank account values, the compiler will instantiate these functions as required. We can tell the compiler exactly what type we want to use by putting a type name between angle brackets, just like we would with something like standard vector. However, a lot of the time with function templates, we don't really need to do this. The compiler can see what types we're passing in as arguments and infer the correct type for t. We can also write class templates, in which the type name gets used in method parameters, return values, or field types. This is exactly how things like standard vector are implemented in the standard template library. And in fact, now we can see why the standard template library is called the standard template library. Instantiating objects of our class templates looks just like instantiating objects of standard template library classes. So that's how we can define function and class templates and how we can instantiate them. There's a lot more to learn about templates, but that's enough to get started on some exercises. One of the most important characteristics of an algorithm is its runtime, how long it takes to do its work. Different algorithms have different runtimes that can vary differently with different data sizes. You've probably heard about algorithms being order n or n squared. In fact, in 1020, we already talked about an n cubed algorithm, but now it's time to get a little bit more rigorous about algorithmic analysis. We will mostly describe an algorithm's runtime in terms of functions of its input size, how much data it's working on. This input size will typically be expressed in terms of the variable n, which represents the number of pieces of data that we're working with. That could be a number of floating point numbers, or a number of objects, a number of students, a number of records that we're processing. The functions of n that we'll see will typically be things like logarithms, linear relationships, quadratic functions, cubic functions, or exponential functions. We'll talk about upper bounds using a notation called big O, lower bounds using a notation called big omega, and exact bounds using a notation called big theta. Let's start with big O. The big O notation means that we can find positive constants that satisfy this inequality. For whatever f of n is, we can find a value of n beyond which our algorithm's runtime is always less than f of n. For example, if f of n is n squared, This means we can find a value of n beyond which the running time of our algorithm is always less than n squared times whatever the positive constant c is. It doesn't matter what the values of c and n naught are. If we can find them, then we can say that this inequality has been satisfied. Let's look at a simple example. In this plot, the dashed black line at the bottom is a linear relationship. It represents a value that grows twice as much for every doubling of input size, for example. Now it would seem that the blue line represents a runtime which grows super linearly, faster than linearly. This looks kind of the same if we look at a bigger picture, where we extend to looking at more data. If we look at an even bigger picture, this still seems to be true, but we see that there's an interesting trend here. Although the blue line is not strictly speaking linear, it's getting closer and closer to linear as we work with larger and larger data sets. If we look at this next picture, we can see that by adjusting the slope of our linear line slightly, we can find a crossover point. Below that crossover point, the blue line is above our strict linear line, but above the crossover point, our blue line is below the strict linear line. We can exaggerate this effect by choosing a larger slope or a larger value of c in the inequality that we saw earlier. It doesn't really matter what the value of c is, and it doesn't really matter what the value of n naught is where the crossover point occurs. The point is that because we can find these constants, this means that the algorithm's runtime is big O n. That is, it's on the order of a linear algorithm. Ignoring constant factors, we can expect that doubling the size of our input data would cause the algorithm to take about twice as long to run. When we increase the size of the input data by a factor of 10 or 100, we would expect the runtime to increase by a similar factor. Again, there may be a constant factor, so increasing by 10 may actually cause it to increase by 20. Increasing the input size by 100 may cause the runtime to increase by 200, but the constant factor is not very important. What's important is that we are increasing approximately linearly with the size of the input, not quadratically, or cubically, or exponentially. So that's the big O notation. It provides us with an upper bound on the runtime of an algorithm. In addition to big O notation, we also have big omega notation, which provides a lower bound on execution time, using exactly the same kind of approach. And we also have big theta notation, which is an exact bound. If an algorithm is big O f of n as well as big omega f of n, then we can say that it is big theta f of n. For example, if an algorithm is cubic in the upper bound and cubic in the lower bound, then it is exactly cubic. We can analyze the worst case behavior of an algorithm by simply counting the operations that it performs. A for loop that iterates through n elements will perform n times the number of operations that are inside of the for loop. When we have loops inside of loops, we analyze them from the inside out. We can see an example of this when we go to class when we'll look at the analysis of the matrix multiplication algorithm. When we have statements that follow each other, we can simply add together the number of operations each performs. Conditional logic such as an if-else results in the worst case of either following the if block or the else block. We have to evaluate the condition and then perform one or the other. Things can get a little bit more complicated when we do a function call, but we need to simply analyze what the function call's performance is first, and then go back to where we were in the broader algorithm. We'll look at a few examples when we get to our class. So that's an introduction to the notation of algorithm analysis, as well as some simple techniques to get started with actually analyzing algorithms. We'll have a chance to practice those in class now. Sorting algorithms give us an opportunity to apply what we've learned about the analysis of algorithms, together with the writing of template functions, as well as an opportunity to review recursion and STL abstractions like iterators. That's a lot of ground to cover. We will look at the venerable but terrible bubble sort, the somewhat better insertion sort, the simple but performant merge sort, the ubiquitous quick sort, and a couple of special purpose sorting algorithms. First, some ground rules. We're going to start by looking at arrays of integers that need to be sorted into a non-decreasing order. In class, we'll work more generally with templates that accept any movable or copyable data type, that is, something with a move or copy constructor. Our templates will also accept comparator functions as parameters, so that we can sort by whatever criteria we like: increasing value, decreasing value, increasing length of a student object's name, etc. Finally, we will use iterators rather than arrays to be as general as possible. To get the basic idea of these sorting algorithms, however, this video will show arrays of integers. The first sorting algorithm you saw in Engineering 1 was the bubble sort. This algorithm takes multiple linear passes through an array, comparing consecutive elements and swapping them if they're out of order. This has the effect of causing the largest number to bubble up through the array until it reaches the end. The algorithm then repeats, causing the second largest element to bubble up and so on. For an n-element array, up to n-1 passes may be required, though the algorithm can exit early if a pass doesn't do any swaps. This indicates that the array is already sorted. The ith pass through the array will perform n-i-1 comparisons and up to the same number of swaps. So, the overall number of operations, in the worst case, is n-1 times a constant times n-i-1, which simplifies asymptotically to n squared. Thus, the bubble sort is a quadratic algorithm. Sorting twice as much data will cost you something like 4 times as much computation. Question: if the worst case of the bubble sort's runtime is quadratic, what is the best case runtime? Insertion sort is another simple algorithm that guarantees progressively larger subsets of a sequence have been sorted. Like the bubble sort, it propagates elements to the place they belong within the already sorted portion of the sequence. Unlike the bubble sort, however, it does this more directly, with an insert-like operation instead of a series of swaps. Still, as an algorithm with order n passes, each of which performs order n operations, this is another quadratic sort. The constant value c may be lower, but it's still a big O n squared algorithm. The merge sort is more sophisticated. It's an example of a recursive sorting algorithm. At first glance, it appears to perform more work than the simple bubble or insertion sort algorithms, but its asymptotic performance is categorically superior. The merge sort takes two already sorted sequences and merges them together into a larger sorted sequence. It is defined recursively. We can sort a sequence of length n if we are given two sorted subsequences of length n over 2. The base case is when n equals 1. Such a sequence is trivially already sorted. The process of merging two subsequences together is linear. The algorithm needs to track the next element in each sorted subsequence and choose the smaller one to add to the larger sequence. This takes order n operations. We will analyze the overall runtime complexity of the merge sort in class, because it's a really neat example of recursion in both the algorithm and the analysis. In practice, owing to high constant factors in the merge sort, some implementations use an insertion sort on small initial arrays, and then use the merge sort to combine them. That's enough to get started with for now. We'll cover more sorting algorithms in the next video. The time it takes to merge sort n elements is the time it takes to merge them, which is linear, plus twice the time it takes to sort each half. The time it takes to sort one element is trivial, or constant time. So now we have an expression in terms of n and t of n over 2, but what is t of n over 2? Well, one way to figure it out is to substitute n over 2 into this original equation. That's going to give us t of n over 2 is equal to n over 2 plus 2 times t of n over 2, which is n over 4. Therefore, if we multiply through by 2, we get n plus 4t of n over 4. Now that we know what 2t of n over 2 is, we can substitute that back into this original equation, and that'll give us the time to do the merge sort on n is n plus 4t of n over 4, or the time it takes to sort a quarter of the data. This simplifies to 2n plus 4t of n over 4. So now we have an expression in terms of n and the time it takes to sort a quarter of the data. But how long is that? We can do the same kind of trick again in order to figure this out, substituting n over 4 into the original equation. T of n over 4 is equal to n over 4 plus 2 times t of n over 8 now. Therefore, multiplying through again, 4t of n over 4 is equal to n plus 8t of n over 8. And now we have the thing we were looking for, the value of 4t of n over 4. We substitute that back in, and now we'll have an equation of t of n is equal to 2n plus n plus 8t of n over 8. That simplifies to 3n plus 8t of n over 8. We can carry on doing this for a while and see that we will get 4n plus 16t of n over 16, 5n plus 32t of n over 32, etc. And eventually we can generalize to k times n plus 2 to the k t of n over 2 to the k, where k is the number of levels of Mergesort calls in the recursion. Suppose we start with 64 elements that we want to sort. That's going to get chopped up into 2, each of size 32. The 32 elements are going to be chopped up into 2 blocks of size 16, etc. The next calls to merge sort will have 4, 2, and 1 elements in them. So that's 1, 2, 3, 4, 5, 6 levels of calls to merge sort. If we erase those and start counting from the bottom up, we'll see that we have 0, 1, 2, 3, 4, 5, 6 levels of calls to merge sort. Every extra level of recursion allows us to handle twice as many elements, so when we add 1 to k, we multiply n by 2. This is an exponential relationship. K is the base 2 logarithm of n, and n is 2 to the k. Substituting this value of kn gives us the log base 2 of n times n plus n times t of n over n. This is n times the log base 2 of n plus n times t of 1. Now we know that t of 1 is just 1, so this simplifies to n log base 2 of n times n plus n. Discarding the lower order terms and ignoring the base of the logarithm, which just works out to a constant, this algorithm's runtime is in the order of n log n. Having looked at the bubble, insertion, and merge sort algorithms, this video will look at the quicksort, counting sort, and radix sort. One of the most common and interesting sorting algorithms is the quicksort. The quicksort algorithm is conceptually simple at the highest levels of abstraction, but there are several important details to get right. Crucially, its runtime performance depends on the first decision the algorithm makes about the input data. The runtime can be big omega n log n, but there are circumstances in which the so-called quicksort can take big omega n squared time to run. The quicksort is another recursive sorting algorithm. Like the merge sort, its recursive step assumes that 2 portions of the sequence can be sorted and then combined. Unlike the merge sort, however, this partitioning is not based on the various elements' original positions in the sequence, but rather on their values. We start by choosing an element called the pivot. If we're very lucky, or very clever, this pivot will be the median value in the sequence, so half of the values being sorted will be less than the pivot, and half will be more than the pivot. Assuming we've chosen a good pivot, and we'll come back to the consequences of choosing poorly, the first job of the quicksort is to partition the sequence into 3 parts: values below the pivot, values equal to the pivot, and values above the pivot. Then, we can recursively sort the small values part and the large values part. Unlike the merge sort, we don't need any temporary arrays to hold values being merged. We just need to be careful about how we move the small and large values around in the sequence, and we can do all of our operations in place. Assuming that we've chosen a good pivot, that is, a pivot which is the median of the values being sorted, the sequence will divide into 2 partitions of equal size, and the complexity analysis will be exactly the same as that of the merge sort. If we choose a bad pivot, however, such as always picking the first element of an already sorted sequence, we will do order n operations to walk through the sequence and confirm it's already partitioned into subsequences of size 0 and size n-1. Then, recurse down n-1 times to do it all over again. In that worst case situation, the quicksort will take n squared operations to do nothing. So, it's clearly important that we choose a good pivot. We could calculate the true median using an algorithm called quickselect, created by the same author as quicksort. But that's another order n operation to do at each level of the recursion, and we can approximate it using a constant time approach, picking 3 elements and taking the median of those. In practice, the first, middle, and last elements work well enough to prevent the pernicious pre-sorted performance problem. The counting sort, or bucket sort, is a sorting algorithm for use with small integers that actually has a linear runtime. In this very simple sorting algorithm, we keep an array of counting buckets as large as the largest value we expect to encounter. We iterate through the sequence and count the number of occurrences of each value, storing the counts in the counting buckets. Finally, we iterate over the counting buckets and put the values back into the sequence. If the value in bucket I is j, we put j copies of the value I into the sorted sequence. A related algorithm is the radix sort, which performs a bucket sort on arbitrarily large integers using a limited number of buckets. In this algorithm, integers are sorted one digit at a time, units, tens, hundreds, thousands, etc. The radix sort can work with any radix, decimal 10, hexadecimal 16, etc., and is linear in the number of elements being sorted times the number of digits in the largest number, which is the logarithm of the largest value. So that's the quick sort, counting or bucket sort, and the radix sort. One of the simplest data structures we'll look at this term is the linked list. We've been introduced to the idea of linked lists before when discussing iterators, but now we'll really dig into the details. Arrays and vectors guarantee that values will be stored contiguously in memory, which makes iteration fast and allocation simple. Containers that store fixed-size data, or that only grow at the end, are ideally stored as arrays or vectors, which are basically just arrays whose memory is managed for you. Arrays are great for iteration and in-place updates, but they are not very amenable to insertion or deletion. Every time you delete an element, all of the remaining elements need to be shifted over by 1 to fill in the space. This is an order n operation. The same is true of insertion. In addition to potentially allocating new memory to store the larger array, you must shift order n elements around to make room for the new element. Linked lists overcome these costs by breaking the assumption of contiguous storage. In a linked list, adjacent sequence elements do not have to be stored adjacent to each other in memory. Instead, elements can be allocated anywhere in the heap. To keep track of them all, each element is contained in an object, a list node, that holds the element and a pointer or two. In a singly linked list, each node has a pointer to the next node in the list. In a doubly linked list, each node has both a forward pointer to the next node and a back pointer to the previous node. Iterating through a list now becomes a matter of following pointers instead of incrementing an index. Iterating through a linked list is an order n operation, just like iterating through an array, but with a higher constant factor. Each step of the iteration involves a pointer dereference and an assignment, instead of just incrementing a pointer or an index. Still, 2n or 3n operations are still order n. The top-level object that represents a linked list will contain a pointer to the node at the head of the list and a pointer to the node at the tail. The simplest option is to have these pointers point at the first and last nodes, or be null if there are no nodes in the list. A more consistent option, however, is to always point at head and tail nodes that act as bookends for the list, rather than members of it. Such nodes are called sentinels, and they can help simplify the list logic because they allow empty and non-empty lists to be treated in the same way. An iterator over a linked list has to be more sophisticated than just a pointer. A list iterator object will keep track of the list node that it's pointing at, and will implement operator methods such as the dereference operator and the increment operators. The increment operators, instead of incrementing a pointer, will dereference the current node's next pointer and set that value to be the new current node. In a doubly linked list, the decrement operators work in the same way, but with the current node's previous pointer. If we have an iterator that points at a specific node in the list, inserting or deleting an element at that location can be done in constant time. First, a new node is created, containing the element, a next pointer, and a previous pointer. Next, the pointers of the surrounding nodes are updated to incorporate the new node. This integrates the new node into the linked list. Deletion is similar. First, we update the surrounding node's next and previous nodes to skip the node being deleted, then we free the memory. Both insertion and deletion require some pointer arithmetic and some memory allocation operations, but they do not depend on the length of the list. That is, they can be done in constant time. So that's how linked lists are stored, iterated over, and modified. We'll have a chance to explore these ideas in our practical class sessions. Another fundamental ADT, abstract data type, is the stack. Just like a stack of plates, a stack is a data structure that accepts new elements on its logical top and offers them from the same place. A stack doesn't provide an insert operation. Instead, it will allow you to push a new element onto the stack or pop an element off the stack. This makes the stack a last-in, first-out data structure. Whatever you pop off a stack is the element you most recently pushed onto it. The term last-in, first-out, abbreviated LIFO, predates the data structure. It's actually a logistics term that was used to describe the warehousing and accounting of inventory, long before anyone had built an electromechanical computer. It's like a moving truck. Whatever you need to have first access to at your new house had better be loaded last on the truck from your old house. The stack only needs to support the push and pop operations, and an operation to peek at the current top value, plus perhaps a method to get the current depth of the stack. This gives us a lot of freedom in terms of how we implement it internally. One option would be to use a linked list, which can give us constant time pushes and pops, assuming we've made some basic design choices sensibly. However, although a linked list can give us constant time push and pop operations, the constants involved are quite high. We don't actually want to do a dynamic memory allocation from the heap for every element that we push on the stack. Instead, it's often better to implement a stack using a vector, an array, or even architecture-specific CPU instructions. What's the cost of pushing to the back of a vector or a manually managed array? Well, I'm glad you asked. The cost of adding to a dynamically growable array, such as a vector, depends on the strategy that we use for allocating memory. Whenever we don't have enough memory to store an element being pushed, we need to allocate a new array, copy the old values over, and then write the new value. One strategy would be to allocate a new array that's one element larger than the old one. This is simple, but it comes at a cost. We will have to do a new allocation and order n value copies or moves on every push. If, on the other hand, we double the array every time we allocate more memory, we can amortize or spread out the cost of the allocations across many push operations. The first push to our empty array will require us to do one allocation and one write of the element being pushed. The next push will require one allocation of size 2, one copy from the old array, and one write of the new element. The next push will cause us to do one allocation, 2 copies, and one write. That allocation buys us a freebie. The next push will only cost one write. We will perform allocations and copies at push 1, 2, 4, 8, 16, etc. up to n over 2 and then n, but all of the intermediate pushes will be pretty close to free. If we add up the allocations, copies, and writes, we can see that each allocation gets us twice as much memory as the one before it, so the size of the array is 2 to the a. Therefore a is the base 2 logarithm of n. C, the number of copies, will be something like n plus n over 2 plus n over 4 and all the way down to 2 plus 1. This is a geometric series of n over 2 to the I from 0 to a, which we know is from 0 to the base 2 log of n. This geometric series works out to approximately 2n. It's actually 2n minus 1, but we don't care about lower order terms. Finally, the number of writes required for n pushes is n times 1 write per push, which is just n. So, the cost of performing n pushes on a doubling vector is log n plus 2n plus n, which is simply on the order of n. That means that the amortized cost of each push is constant time. Stacks are useful for tracking all kinds of information, including arithmetic, parts of program parsing and expression evaluation, and calling functions. Remember that local variables in C++ programs are stored in a memory region called the stack. This is a super optimized version of the generic data structure that we're looking at. Stack operations are so common that CPUs provide dedicated instructions for pushing and popping CPU registers to and from the stack. One thing to be aware of, although stacks logically grow from bottom to top, CPU push and pop instructions typically assume that stacks grow downwards. Now that we know how to make trees, let's talk about how to do things with them. We might want to evaluate trees that describe expressions, render hierarchical user interfaces held in trees, or even just print out the values in a tree. All of these are examples of tree traversal, which means iterating over tree nodes and doing something with them. Tree traversal is a good topic to help us understand trees better and practice writing recursive algorithms. When we iterate over arrays, vectors, or linked lists, we do a nice linear walk through a nice linear data structure, and it takes nice linear time. We would like tree traversal to also be linear in the number of nodes. In a single traversal of a tree, we only want to visit each node once. However, it turns out that there are several different ways to do this. Starting from the root node, we can traverse child nodes in either a breadth-first or a depth-first fashion, and there are 3 depth-first traversal orders: pre-order, in-order, and post-order depth-first traversal. Let's talk about each of these strategies in turn. First of all, we can traverse a tree in level order, also known as breadth-first. In this traversal strategy, we perform an action on all of a node's children before performing that action on their children. This action can be anything from printing a value to some heavy-duty computation, and it depends on the type of value we're storing in the tree. We'll talk about one specific example, printing out nodes in a programming language's abstract syntax tree, later in this video. We refer to performing an action on a node as visiting the node. Note that we don't have to visit a node and its children at the same time. In a level order traversal, we visit a node and enqueue its children for later visitation, after we're done with the current level. The other broad category of tree traversal is the depth-first traversal. This category of traversal is amenable to recursion since it's concerned with processing subtrees. We can do depth-first traversal with a pre-order, in-order, or post-order algorithm. In a pre-order traversal, we visit a node before visiting its children. This leads to nodes being traversed in a fairly intuitive order, one that lends itself to printing information about nodes from top to bottom, or to setting up resources required by child nodes, such as buffers to render UI components into. In a post-order traversal, we visit a node's children before visiting the node itself. This allows child nodes to have input into the visitation of the parent node. For example, in order to tell how much space is being used by a directory on your hard drive, software must first look at everything inside of that directory and determine how much space it is using. That process can carry on recursively until we are ready to summarize an entire subtree. In-order traversal only really makes sense for trees that have a more regular structure than we've imposed so far. We'll come back to in-order traversal when we talk about binary trees. One super practical example of tree traversal is printing out source code. When source code written in a language like C++ is compiled into machine code, one of the first steps the compiler has to take is to convert the source text into a tree that represents the structure of the program. This tree is called an abstract syntax tree, or AST, and modern compilers give us tools for inspecting the AST directly. In this example, we'll look at one of the simplest possible C programs that does something. We don't include any header files because they would make the AST much more complicated. Instead, we just have a couple of numerical functions, main and foo. We can compile this to an object file with the C option, or we can just run some syntax checks with F syntax only. With the Clang compiler, we can also pretty print the AST that the compiler has parsed using the AST print option. Note that this printed AST doesn't include comments or whitespace from the original source code. This is a representation of just the compiler meaningful information stored in the AST. This is even clearer if we use Clang's AST dump option, which shows us the explicit tree structure of the parsed program. For example, the main function has one child, a compound statement, that has 2 statements in it. One is a variable declaration decl statement, and the other is a return statement. Each of these statements has child AST nodes that describe the variable, how it's initialized, what value to return, etc. The foo declaration has 3 parameters, so the foo function has 3 parm_var decl children, plus a compound statement representing the body of the function. This explicit tree representation is exactly how a compiler represents source code in memory after it's been parsed. So that's tree traversal. We've discussed breadth-first and depth-first approaches, including pre-order and post-order traversal. We'll come back to in-order traversal when we talk about binary search trees, which should be our next topic. The binary search tree is a crucial data structure that will give us the chance to practice writing recursive code. A binary tree is one where each node has 0, 1, or 2 children. As a specialization of the more general tree, a binary tree lets us optimize the representation. Each node need only have 2 child pointers called left and right. But equally importantly, it allows a new tree traversal strategy. We saw pre- and post-order traversal in the previous video. But with binary trees, we can also use an in-order traversal. In this traversal strategy, to traverse any node, we first traverse its left subtree recursively, then we visit the node in question, then we traverse the right subtree recursively. This has the effect of visiting all the nodes in the tree, in order, from left to right. A binary tree can be used to represent things like expressions involving unary and binary operators. This covers a lot of ground, as most of the operators that we care about are unary or binary. However, it doesn't quite cover all of the expressions that matter. C, C++, Java, and other languages also implement ternary operators for conditional expression evaluation. It's not pretty, but it's real. Every node in a tree has a depth and a height. The depth is the length of the path from the tree's root to the node. The height is the longest length of the path from the node to a leaf. The height of a tree is the height of its root. You will sometimes also hear this referred to as the depth of the tree. If the heights of each node's subtrees are equal, or at least pretty close, we can call the tree balanced. A balanced tree has the neat property of a logarithmic height. The length of the path from the root to any node in the tree is order log n. This property only holds for balanced trees. It's possible to make trees that are unbalanced to the point of being, in the degenerate case, linked lists. Some of the types of trees that we'll look at after the midterm break will impose additional structure on binary trees to ensure that they stay balanced. If we specialize a binary tree by adding an ordering constraint on the nodes, we end up with the ubiquitous binary search tree. In a binary search tree, every node has the property that values smaller than its own are in its left subtree, and values larger than its own are in its right subtree. This means that every subtree within the tree is sorted. This allows us to search for values in the tree faster than linearly. To search for a value within the binary search tree, we start at the root and check to see if the value we're looking for is less than the root node's value. If it is, we recursively search the left subtree. If, on the other hand, the current node's value is less than the one that we're looking for, we recursively search the right subtree. If neither is true, then the current node must contain the value we're looking for, and no further recursion is required. Since the tree is sorted, we never have to look at a subtree that doesn't contain the value we're looking for. There are no false starts, and the maximum number of recursions is equal to the height of the tree, which in a balanced tree is on the order of log n. If we need to look through a tree of 1,000,000 elements, we would expect to perform just 20 comparisons and recursive descents. Note that this binary search only required that we be able to compare values and ask whether one is less than the other. We don't even need to be able to compare directly for equality. This simplicity of comparison allows us to define all kinds of comparisons. For example, we can compare transcripts based on one course, another course, or even a number of courses together. In fact, a useful exercise would be to create a binary search tree that uses a non-trivial comparison function, such as one that compares a particular field within two objects. Finding the minimum or maximum value in a binary search tree is fairly trivial. Just keep following left or right pointers until you reach the end. Insertion is a more interesting operation, but not terribly complex, if you think recursively. Starting at the root of the tree, we compare the new value to the current node's value. If it's less than the node's value, we need to insert on the left, keeping in mind that adding to an empty tree is a matter of creating a new node and setting the subtree's root to point at it. If the current node's value is less than the new value, we need to insert on the right. If neither is true, the new value is equal to the current value, and we can increment a counter in the node, add the new value to a linked list hung off the node, or in some cases, simply ignore the new value. In a balanced tree, again, insertion should take logarithmic time, although the insertion may cause the tree to become less balanced. That's all we'll talk about for now. After the break, we'll look at how to remove elements from a binary search tree, and then we'll talk about more specialized trees such as AVL trees, which work to keep the whole tree balanced to preserve logarithmic search times. Removing a node from a binary search tree is slightly more complicated than inserting one. We saw in the previous video that the only interesting part of node insertion is figuring out where to perform the insertion. We can do this with a recursive algorithm that either inserts the node here, for some definition of here, or else it calls itself recursively on the left or the right subtree. Once nodes are in place, we can look them up by recursively descending through subtrees, based on whether the node we're looking for can be seen as less than or greater than the current node. Removing a node is going to build on this lookup algorithm by doing some work after we find our node. How much work will depend on the topology of the node we need to remove. In order to remove a node, we first have to find it. In a binary search tree, we can do this by recursive descent just like a normal search operation. Just like searching, the base case for our recursion will be when we reach a node that doesn't exist. If our recursive descent through the search tree has hit a dead end, a tree must not have the node we're looking for, so we're done. Question: why don't we need to look elsewhere in the tree? Use a couple of examples to convince yourself. If the value we're looking for is less than the current node's value, we can recurse down through the left subtree. If it's greater, we recurse down through the right subtree, although we actually test whether the node's element is less than the value, so that we only need the one comparator. If none of the above are true, that is, we have a non-null node whose element is neither less than nor greater than the value we're looking for, then we have found the node to remove. We now have to consider a couple of cases. The most complicated of these is when we want to remove a node that has 2 children. We can't just add these children to the parent node. Then there'd be a node with 3 children, so it wouldn't be a binary tree anymore. This is a slightly special case, so actually we're going to come back to it. If the node to remove doesn't have 2 children, then it must have either 0 children or 1 child. If it has 0 children, that's easy. We can just remove the node. If it has 1 child, that's also pretty easy. We can update the pointer to this node to point at the child instead, skipping over the current node just like we would in a linked list. In fact, we can handle these 2 cases, either 0 children or 1 child, using the same code. We update the pointer to the current node to take the value instead of one of the current node's child pointers. That new value may point at a real node or it may be null, but either way, the current node pointer has been updated correctly. If you don't see how that's the case, take this code and try to work through what it does with a couple of pen and paper examples. Remember that we're using smart pointers here, so we don't need to explicitly delete the node being removed. Changing the pointer will take care of that for us. Also, note that the ternary if operator has come back to haunt us. Now would be a good time to pause the video and check your comprehension by explaining this partial method implementation to someone else, even if that someone is just imaginary. Believe it or not, explaining things to people, even imaginary people, is a great way to test your understanding of all the finicky details. Go ahead and do that now. Now that you've explained this straightforward stuff to someone, let's come back to that special case, removing a node with 2 children. We can't just change the current node pointer to point at one of the children without discarding the other one. So what can we do? One simple answer is to replace the current node with a node from one of its 2 subtrees. But how can we choose a node to replace the current node that preserves the search property? What node could we choose that wants to keep all of the left subtree on its left and all of the right subtree on its right? The answer is either the maximum value in the left subtree or the minimum value in the right subtree. If we simply move that node's value into the current node, we will remove the current node's value while maintaining our binary search tree invariance. We do need to make sure that we tidy up the old node whose value we are stealing. So that's how to remove a node from a binary search tree, whether that node has 0, 1, or 2 children. We'll practice implementing this algorithm in our class time together. In this video, we'll build on the concept of binary search trees by introducing the AVL tree. This is a binary search tree that keeps itself balanced when you add or remove nodes. Binary search trees work really well when they're balanced. When searching for a node in a BST, every step we take deeper into the tree reduces the number of nodes we need to consider by half. Put another way, the number of nodes that we can look through in k steps is 2 to the k. If n equals 2 to the k, then k is the base 2 logarithm of n. So a search through a balanced binary tree is an order log n operation. However, adding and removing nodes can cause a binary search tree to lose its balance. In the worst case, we can turn a balanced tree into a linked list with order n performance for search, insertion, and removal. To avoid this worst case behavior, we would like for our trees to be self-balancing. The first self-balancing tree was invented in 1962 by 2 Soviet mathematicians named Adelson-Velsky and Landis. This tree is called an AVL tree. Can you see why? The AVL tree adds one more constraint to our binary search tree. Not only does it have to be binary, and not only do each node's left and right subtrees have to be partitioned by the node's value, now we also have the constraint that every node's subtrees can differ in height by no more than 1. Here's an example of an AVL tree with 4 nodes. Adding in each node's height, we can also see each node's balance factor, the difference between the heights of the node's 2 subtrees. When we insert a new node in the tree, we update the height and balance factor for each node along the way. We can do this by returning the change in height from each recursive call to insert and using this in the parent node to update its height and balance factor. In reality, we only really need the balance factor, not the height, but we'll include heights here for clarity. Anyway, once we get to node 17, there is a problem. The balance factor is now -2, which is outside of the plus or minus 1 range allowed by the AVL constraint. To keep this an AVL tree, we have to do something to rebalance the tree. Rebalancing in this situation can be accomplished by a single rotation of the subtree rooted at 17. First, we decide which of 17 subtrees has the greater height. Since the balance factor here is negative, we know that the left subtree rooted at 8 has the greater height. We then take that left subtree and make it the root of the subtree that used to be rooted at 17. Finally, we complete the rotation by making the old root of the subtree, that is 17, the right child of the new subtree root, 8. Once we do this, the new height of the subtree ends up being exactly what it was before the insertion, so there are no further height adjustments to make on parent nodes. Here's another example, this time generated from visualgo.net. This visualization doesn't include balance factors, so take a moment now to annotate it with heights and balance factors, maybe in your notebook. Once you've done that, figure out where the number 2 would be inserted in this tree and how that would affect the heights and balance factors of the other nodes. What is the root of the subtree that requires rotation? One key difference between the last example and this one is that the new subtree root, 4, already has a child node on its right, the 5 node. When we rotate 4 up to the subtree root and 6 down to the right of 4, where can the 5 node go? Pause the video again and take a moment to work this out. Continuing on, we see that the right child of the new subtree root becomes the left child of the old subtree root, occupying the pointer that used to be used for the node, which is now the subtree root. That probably sounds a little confusing. So go ahead and watch those examples again as many times as you need to in order to really understand what's going on. In a moment, I'll encourage you to try out more examples yourself on visualgo.net, but before you do, a word of caution. So far, we have looked at examples in which a newly inserted node appears to the left of the left child of the node that wants rebalancing. In such cases, all we have to do is a single rotation to the right. You can probably imagine that the mirror image is also true. If we add a node to the right of the right subtree of a node and cause its balance factor to become +2, we need to do a single left rotation. We can call these newly inserted nodes outer nodes, since they appear on the outside edge of a subtree. If we add an inner node, however, we have to do something slightly more complicated, which we'll discuss in the next video. So, I suggest that you go off now to visualgo.net/bst, click on AVL tree, and try out a few examples of doing left-left or right-right insertions. Try creating a tree, choosing a value to add, predicting how the tree will be rebalanced, and then using the visualization tool to check your prediction. Once you understand the idea of single rotation, we'll practice the implementation in our next class. In the last video, we saw how a single rotation can help an AVL tree maintain its balance property when we insert new outer nodes. However, a single rotation isn't always enough to maintain the balance of an AVL tree. When we violate the AVL balance property by insertion of an inner node, that is, the right child of a left node or the left child of a right node, a single rotation doesn't actually fix anything. If we follow the rotation rules from the last video, we will end up grafting the new node onto a node, which used to be the pre-rotation subtree root, at the same depth in the subtree. A left-right node becomes a right-left node, but it remains an inner node at the same depth. To fix this situation, we first need to arrange for our subtree to be too deep in an outer node rather than an inner one. Once we have that situation, we'll be able to fix it through the kind of rotation that we saw in the last video. So how do we convert a tree with a too deep inner child into one with a too deep outer child? Through rotation. Here we see an inner node insertion that causes a subtree to go out of balance. We can't directly fix this situation, but we can put ourselves one step closer to solving the problem. If we perform a left rotation on the subtree rooted at 4, we will still end up with the tree rooted at 17 being out of balance. but now it's out of balance thanks to an outer node rather than an inner node. This is a problem we know how to solve. We can fix this by applying a right rotation to the tree rooted at 17, and we end up with a balanced tree once again. So, when we are out of balance due to going too deep with an inner child, we need to perform a double rotation. Once to get into a situation with a too deep outer child, and once more to rebalance the tree. Question: what is the complexity of performing this double rebalancing in terms of the number of nodes in the tree? So now we've seen what an AVL tree is, and how it maintains its balance through all sorts of insertion operations. We may also need to rebalance using exactly the same single or double rotation techniques when we remove a node that throws us out of balance. Take a few moments now to practice visualizing these kinds of rotations using visualgo.net. Just as before, start by planning a tree that you want to insert into or remove from, then predict what the effect will be, then use the visualization tool to confirm your hypotheses. Next, we'll practice writing this code in class. The next data structure that we're going to consider in this course is the graph. A graph is a data structure that contains vertices and edges. The edges that connect vertices may be directed, that is, they point from one vertex to another, or undirected, that is, they simply indicate that two vertices have a connection. Both types of graphs are useful for representing both virtual and real-world networks. Directed graphs can represent the flow of packets in a network or other kinds of unidirectional information flow. The computers in the network are vertices in the graph, and the packets or other messages they transmit are the edges. Some transportation networks, such as the air transportation network, can be modeled as directed graphs, in which the vertices are airports, and the edges are flights that you can take between those airports. Even social networks can be modeled as directed graphs, in which people are the vertices, and communications among them, letters, emails, text messages, are edges. Undirected graphs are useful for representing lots of things too. Electric circuit netlists, transportation networks with two-way travel, and social networks viewed from a slightly different perspective, in which people are either friends or not friends, and friendship is always a two-way street. The route we can take to get from one vertex to another in the graph is called a path. A path may contain multiple edges. The length of a path is the number of edges that it includes. There may be many paths between two vertices. There's more than one way to fly from Vancouver to St. John's. This is especially true when we consider cycles, paths that go through the same vertex more than once. Although this diagram only shows eastbound flights, you could fly back and forth between Toronto and Montreal all day long if you wanted to, adding 2, 4, 6, 8 or more segments to your trip. You wouldn't want to do that, but you could. The number of edges that a vertex touches is called its degree. A high degree vertex is one that is involved in a lot of edges. In a directed graph, we can split a vertex's degree into in degree, the number of edges pointing to the vertex, and out degree, the number of edges pointing away from it. This graph shows the in and out degree distributions of English Wikipedia articles, where the vertices are articles and the edges are hyperlinks among them. From this graph, we can see that articles tend to have higher in degree than out degree. There are a few articles that are linked to from tens or even hundreds of thousands of other articles, but we don't see articles that link to tens of thousands of other articles. This should intuitively make sense to us. A graph is a very general concept, but there are a few special cases that are worth understanding. First, when a graph has no cycles in it, we call it acyclic. Directed acyclic graphs are so common that we often refer to them by the acronym DAG or DAG, Directed Acyclic Graph. Among other things, DAGs can be used to represent dependency graphs, which express the dependencies that various parts of a project or process have on other parts. These graphs are used extensively in project management, sometimes illustrated with a Gantt chart, but we've already seen some examples of dependency graphs in this course, makefiles. One of the most fundamental things that a makefile does is to specify which files depend on which files, so that we can rebuild only those things that actually need to be rebuilt when we change, for example, one source file within a large project. A further specialization of DAGs can be found when every vertex has an in degree of no more than 1. In that case, the graph that we end up with is actually a tree. If we specialize further by limiting every node to an out degree of 1, we end up with a linked list. When we want to actually build a graph data structure, we have one important choice to make quite early on: how to represent the edges. Representing vertices is fairly straightforward. We will need some kind of iterable container, whether that be a linear data structure or something like a binary search tree that can be used to efficiently look up specific vertices by a name. When choosing a representation for the edges, however, we have to choose between two main approaches. The first is an adjacency matrix. An n by n matrix, where n is equal to the magnitude of v, the number of vertices in the graph, in which the space at ij can be used to indicate whether or not there is an edge between vertices I and j, or, in a more sophisticated design, where to find the object that represents the edge between I and j. The adjacency matrix approach works well for dense graphs, which are highly connected. Most graphs, however, are not dense but sparse, with many fewer edges than would be theoretically possible. For example, many social networking sites have millions or even billions of users, but most of those users do not have millions of connections to millions of other users. When a graph is sparse, we will often prefer an adjacency list holding all the edges, or multiple adjacency lists, with each vertex holding a list of its edges. So then, graphs are data structures with vertices and edges. They can be directed or undirected, and their paths can be cyclic or acyclic. Each vertex has a degree, and if we constrain the degrees of the nodes, we end up with special cases like trees and linked lists. A graph representation can store its edges in an adjacency matrix, an adjacency list, or in multiple adjacency lists. That's enough of the basics for now to get you going. Let's try our hands at some exercises. One of the things we need to be able to do with a graph is to find the shortest path through it. All other things being equal, we usually want to drive the shortest distance, take the fewest flights, or use the fewest communication links that are required to traverse a graph. Let's start by looking at an example of finding the shortest path from a source vertex in an unweighted graph, that is, one where every edge is counted simply as an edge, not as an edge of a particular distance, to any other vertex in the graph. One way to do this is the algorithm being displayed now. In this algorithm, we start by assuming the distance from the source to any other vertex is infinite. We also mark each vertex as not having been looked at yet. Please note that we're showing all of these properties as fields of the vertices to keep the pseudocode simple, but in reality, we'd store a table of distances, paths, and done flags separately from the vertices, so that we could ask questions about shortest paths from various starting vertices. Once we've initialized our table, we start from the source vertex, looking at all of its neighbors and setting their distances to 1, then looking at each of those vertices in turn, looking at their neighbors, etc., until we've considered all the vertices in the graph. By only considering vertices that are the same distance away from the source, we expand the search for vertex depths in growing concentric rings. This is called a breadth-first search, and it stands in contrast to the depth-first searches that we've been using for things like tree traversals. Let's take a look at a visualization of this algorithm. Here, we're using an undirected graph, but the same algorithm would apply in a directed graph. First, we consider the starting vertex with a depth of 0 and look at each of its neighbors. We set the distance for each neighbor to 1 and set the path to the neighbor itself. This means that to get to vertex 2 or 5, we can move directly to vertex 2 or 5. Once we've considered all the neighbors, we can mark the source vertex as done and move on to vertices with a depth of 1. We consider each of these in turn, ignoring any vertices that we've already finished with, in this case, vertex 1. We carry on considering vertices of depth 2, 3, 4, and finally 5, at which point we've finished exploring the whole graph. What we're left with is a table that tells us how far away every vertex is from a chosen source, and how we could get to any vertex via the shortest path, one vertex at a time. If we add weights to the edges, we end up with Dijkstra's algorithm for computing shortest paths. This algorithm assumes that we can keep track of how many vertices haven't been completed yet, pretty straightforward, and that we can select the undone vertex with the smallest distance. Then, the only remaining change is that we need to update a neighboring vertex's path if its distance is not necessarily infinite, but just greater than the distances of the current vertex and the current edge combined. We'll talk about the analysis of these algorithms next week. For now, we'll work on implementing them correctly. When we know that a graph is acyclic, we can do a couple of interesting things with it that we can't, in general, do to just any old graph. In our recent classes and exercises, we saw that Dijkstra's algorithm can find the shortest paths from a source vertex to all other vertices in on the order of the size of v squared operations, with a linear data structure holding the vertices, or on the order of size of v plus size of e log size of v, with something like a binary search tree or binary heap holding them, arranged by distance. If we happen to know that there are no cycles in the graph, however, we can do quite a bit better than that. Just observe how we can traverse this graph, discovering new vertices as we go. Every vertex will only be visited once, and if we add the vertices to a work list in a very particular order as we first discover them, we don't need to search for the best vertex to visit next. We can just look at the next one in the work list. Visiting, or arranging, vertices in this way is called a topological sort, and its asymptotic runtime complexity is on the order of the size of v plus the size of e. I mentioned a very particular order in which we need to add the vertices to the work list. We want to add vertices to the work list only after we visited all of their predecessors. We can keep track of this by tracking the in degree of each vertex, that is, the number of edges pointing towards it, and decreasing that number whenever we visit a vertex that has an edge pointing at it. When that number reaches 0, we have considered all the vertices that can precede the vertex in question, so we can add it to the work list. In tomorrow's exercises, I'll ask you to think about and sketch out an algorithm for doing this kind of topological sort. I'll also ask you to analyze its asymptotic runtime performance. Another important kind of analysis for acyclic graphs is critical path analysis. We've previously said that directed acyclic graphs can be used to model things like software build dependencies, but they can also be used to model dependencies in project management. This graph shows a representation of tasks that might be included in a project, and how long each task will take. Each vertex represents something that we need to spend time doing. Each edge represents a dependency from one task to another. For example, you can't raise funding from angel investors until you've written a proposal. To do a critical path analysis, we'll start by converting this graph into a representation that shows milestones instead of tasks as vertices. Now every vertex represents the completion of some part of the project, and the edges represent how long it will take to get from a previous milestone to this one. We can calculate the earliest possible time for each task to be finished by analyzing the shortest paths from the start vertex to every other vertex. Because it's an acyclic graph, this should be a linear time operation. Once we know how soon the entire project can be completed, we can work backwards to find out the latest possible time for each milestone to be completed without affecting the overall completion time. Then we can calculate schedule slack, how late each milestone can be without delaying the overall project. Some milestones will have 0 slack, and a path that goes through only 0 slack milestones is called a critical path. If anything on a critical path is delayed, the entire project will be delayed. Tracking critical paths is an important task for project management software. We've now seen how acyclic graphs provide us with the opportunity to do more, or to do it in less time. We can find the shortest paths from a vertex in an acyclic graph in linear time, and we can also perform critical path analysis. Let's look at these in more detail in our class together. Some vertices in a graph are more important than others. One way of describing a vertex's importance is centrality. The simplest measure of a vertex's centrality is degree, the number of edges that are connected to a vertex. In a directed graph, we can separate degree into in degree and out degree, which measure exactly what you would think, the number of edges directed into and away from a vertex. Degree is quick and easy to calculate, but its value can be limited. The number of social network friends someone has doesn't necessarily tell you much about their importance in the overall network, their influence, etc. A more sophisticated measure of centrality is betweenness centrality. This is a measure of how many of the shortest paths through a graph flow through a particular vertex. More formally, it's the ratio of the number of shortest paths in the graph from all possible starting to all possible ending points that flow through vertex V to the number of all shortest paths through the graph. If you wanted to observe the largest number of messages flowing through a network, you'd start by monitoring the vertices with the highest values of betweenness centrality. The cost of computing betweenness centrality is dominated by the cost of calculating the shortest paths from all vertices to all other vertices. In a dense graph, The Floyd-Warshall algorithm can find all such shortest paths in on the order of v cubed time. In a sparse graph, algorithms like Johnson's algorithm do something like running Dijkstra's algorithm v times. If the graph is unweighted, Brandis's algorithm can compute all shortest paths in just order v times e time. Degree and betweenness centrality are critical to social network analysis, the study of how people and groups interact with each other at a systemic, rather than individual, level. Social network analysis turns out to be important in areas you'd expect, like sociology, but also in areas you might not expect, like criminology. Traditional thinking about organized crime modeled criminal organizations as trees, always trying to get the people at the top. The problem is, if you remove someone at one rung of the ladder, there are always others ready to step up and fill the gap. Many law enforcement agencies are now turning to social network analysis to identify individuals that are very central in such networks, even if they aren't in charge. A highly central individual may be difficult to replace, causing disruption and lessening criminals' ability to organize. Social network analysis is also key in terrorism investigations, though the acceptable uses and limits of this analysis are key points of contention between governments and privacy advocates. Another family of centrality measures is eigenvector centrality. These measures attempt to model the influence of vertices within a graph. We won't get into the details of these algorithms, but in addition to social network analysis, they are important for assessing the importance of linked knowledge artifacts like scientific papers and even web pages. Google's PageRank algorithm is a modified version of eigenvector centrality. So that's a few ways to measure the importance of vertices within a graph: degree, betweenness centrality, and eigenvector centrality, as well as how these measures are applied to social network analysis and influence modeling. A recursive search through a graph is called a depth-first search. Depth-first search is a generalization of the recursive traversal algorithms that we use with trees. Just like tree traversal, depth-first search involves recursively visiting the neighbors of vertices, such that we visit neighbors of one immediate neighbor before we visit the next immediate neighbor. This is in contrast to the breadth-first search that we saw with unweighted shortest path algorithms, where we visited all of a vertex's immediate neighbors before we visited any neighbors of neighbors. A breadth-first search looks like expanding concentric rings. A depth-first search looks more like a tree traversal. In fact, tree traversal is just a special case of depth-first search, where each vertex in a graph has a maximum in degree of 1. In the more general depth-first search, however, we need to pay a little more care to some particular details. In a tree traversal, we don't need to explicitly keep track of which nodes we've visited because there's only one way to get to a node. In the more general case of graphs, however, there can be multiple paths to a vertex. One trivial example is that of a cycle, which might lead us to visit a vertex an infinite number of times in a loop. We can stop ourselves from visiting a vertex multiple times by keeping track of the vertices we've visited. Armed with that extra bit of information, which we can store in a table or even write in the vertex itself, we can ensure that we only visit each vertex once, and, if we use an adjacency list representation, the total operations can be kept to the order of the size of v plus the size of e. See if you can figure out why this is the asymptotic time complexity of the algorithm. In just a moment, we'll look at it together. Here's a sketch of the algorithm to do a depth-first search. First, we mark the current vertex as visited, and then we check all of its neighbors to see if they've already been visited. If not, we do a recursive depth-first search on them. In this algorithm, we can see that we only visit vertices that haven't been visited before. Also, we mark the current vertex as visited before we have any opportunity for recursion. Therefore, we can only ever visit the size of v vertices at maximum. Next, we observe that, in any connected graph, if we visit a vertex while there are n unvisited vertices, that visitation will cause another n-1 visitations to occur. This is true whether the graph is linear, radial, or some other topology. Every recursive depth-first search will cause another n-1 searches to occur, assuming only that all vertices are reachable from the current vertex. Finally, armed with this information, we can write a recurrence relationship for the time it will take to complete a depth-first search. This time is on the order of 1 for the marking of v as visited, plus the time to check out all of our neighbors. Inside of this loop, we see potentially many recursive depth-first search calls, but we've already said that we know what those add up to, the time it takes to visit n-1 additional vertices. What's left of the loop is checking all of a vertex's neighbors, which is on the order of the number of neighbors, which I'm calling e sub I, where I is the number of the current vertex. So, the total time to visit vertex I with size of v vertices remaining, including I, is 1 plus the size of e sub 0 plus the time it takes to visit the size of v minus 1. We can use the same equation to expand out the time of the size of v minus 1 vertices, then the time of the size of v minus 2, etc., until we end up with the sum of all of those ones, 1 per vertex for a total of the size of v, plus the sum over all vertices of each vertex's edge count, which is just the number of edges in the graph. Depth-first search has many applications. In this video, we'll mention 2, spanning trees and circuits. A spanning tree is a partial representation of a graph, which includes all of the vertices of the full graph, but only just enough edges, in the shape of a tree, to be able to reach all of the vertices from a root vertex, or node. One kind of spanning tree, a minimum spanning tree, can be built using Prim's algorithm, which is almost exactly the same as Dijkstra's algorithm. It's called a minimum spanning tree because it involves minimum cost, or shortest, paths from a root node. However, we can also construct a spanning tree using depth-first search. In this approach, we perform a depth-first search and, anytime we find an edge to an as-yet unvisited vertex, we add that edge and vertex to our spanning tree. If we start with a graph containing disconnected components, we can repeat the process to end up with a spanning forest. Another application of depth-first search is finding circuits in a graph. The very first graph theory problem, postulated before there even was such a thing as graph theory, was finding a path through a graph that would pass through every edge once and end up back where it started. You may have seen this as a puzzle in which you need to draw a geometric shape without lifting your pencil or redrawing any lines. There are 2 variations on this problem, one in which you have to end up back in the place you started, and one in which you don't. Leonhard Euler solved this problem in 1736, giving us Euler tours and Euler circuits. Euler circuits are only possible when all the vertices in a graph have an even degree. Question: why is this so? Take a moment to think about it. It turns out, however, that an even degree is not just a necessary condition, it's sufficient. In any such graph, we can find an Euler circuit using repeated depth-first search. First, we pick a vertex, any vertex, and perform a depth-first search until we find an edge that leads back to where we started. This gives us a circuit. There's no guarantee that this circuit will go through all the edges in the graph, but it's a start. If there are unexplored edges in the graph, at least 2 of them will have to connect to a vertex that is part of our circuit. We can iterate along our circuit until we find a vertex with unexplored paths, and then follow the same depth-first search procedure to find another circuit that starts and ends at that vertex. We can then graph the newly found circuit onto our prior one, giving us a longer circuit. We can continue repeating this procedure until all of our edges have been found and integrated into a complete Euler circuit. If we're careful in our choices of data structures and algorithms, we can find Euler circuits in linear time, on the order of the size of v plus the size of e. Finding Euler circuits, which traverse every edge in a graph, is, thus, surprisingly easy in graphs that contain them. An analogous problem is finding circuits that contain every vertex in a graph. Such paths are called Hamiltonian cycles, and in general, it's not so easy to find them. In fact, it's hard. It's really hard. In general, it's really, really hard. How hard? We'll talk about that next time. That's depth-first search and a couple of applications for it. Building depth-first spanning trees and finding Euler circuits. Next time we'll talk in more detail about Hamiltonian cycles and just how hard a problem it is, in general, to find them. In this video, we'll introduce the hash table, a simple but extremely useful data structure. Thus far in the course, we've seen a number of data structures for storing values. Contiguous data structures, arrays and vectors, support constant time lookup by index, but linear time search. Insertion and removal time depends on location. In general, they're linear. Linked lists improve on this by providing constant time insertion and removal, but search is still linear time. Search trees, of which we focused mainly on BSTs, provide logarithmic performance for insertion, removal, and search. In the C++ standard library, Standard map and standard set are usually implemented as binary search trees. Search trees, including those used by the STL, are fundamentally ordered based on comparison. A node's place in a tree is determined by how its value, or in the case of nodes with both a key and a value, its key, compares to other nodes in the tree. This ordering is based entirely on a comparator, less than, greater than, student number is greater than, etc. The ordering can also be used to provide ordered traversal over the tree, whether over the entire tree or just portions of it. For example, please iterate over all of the students with student numbers between this one and that one in order of student number. This can be a very handy ability, but sometimes we don't really need ordering. Sometimes we just want to be able to insert, look up, and remove things as fast as possible. Can we make these operations any faster than logarithmic if we're willing to sacrifice ordering? Well, I'm glad you asked, and yes, we can. We can, in fact, get constant time performance if we don't need ordering. The hash table is a data structure that provides constant time insertion, lookup, and removal of elements that have two properties. They can be checked for equality, and each can be processed with a hash function to produce an integer hash code. This is a more complex requirement than for search trees, where only a comparator needs to be defined, but the benefits are worth it. Equality is what you would expect, a test of whether or not two values, or two keys, are the same. What's new is the hash function that produces a hash code. A hash table stores values in an array, but instead of adding each new element after the previous one, it is added at an index derived from the element's value. This index is the hash code produced by a hash function. A hash function calculates a hash code for an element. If we choose a good hash function, every value will hash to a different code. A very simple example of a hash function is one that distributes numbers across a hash table with n cells by computing x mod n for any given x. In this example, the number 407 hashes to 4, 218 hashes to 10, etc. So that's where we put these numbers in the table. If we want to look up 218 later, we compute the hash of 218, get the number 10, and go check that place in the table. If it's there, then we found it. Otherwise, it's not present. Note that, unlike a comparator-based data structure like a binary search tree, we can't find the next smallest or next largest value to the one we're looking for, but in many circumstances, we don't really need that information. In this simple example then, adding, finding, or removing a value can be done in constant time. Not all uses of hash tables are quite that simple, however. In fact, few are. For example, say that we want to store some strings in a hash table, or equivalently, we want to store some key-value pairs in a hash table where the keys are strings. Now say that we want to use this simple hash function. We take the first character of the string and subtract a from it, then calculate the remainder of that divided by 26 to ensure that non-alpha values won't hash to negative values, etc. We can store common names like Alex, David, and Heather quite straightforwardly. But what if we try to add an Andrew to the mix? In that case, we will encounter a hash collision. Two different values hashed to the same index. Now, this example hash function is actually quite terrible, but even with a much better hash function, there will still be collisions. We need a strategy for resolving these collisions. One strategy for resolving hash collisions is chaining. Instead of storing a single element in each cell or bucket of the hash table, we store a list of elements. Then, if we encounter a collision, we just append the element to the appropriate list. The average length of these lists is the ratio of the number of elements in a hash table to the size of the table. This ratio is called the table's load factor, denoted lambda. If the hash function distributes the elements fairly evenly, we will usually have to traverse a list of lambda elements to find the one we're looking for. If our hash function doesn't do a good job, the situation can be much worse. Look at how many collisions the previous hash function would cause if we fed it one list of 200 popular baby names. Not only are there lots of collisions, some initials are much more collision prone than others. A better example of a hash function for a string is shown here. It's still pretty simple to calculate, but it leads to a much more even distribution across the lists stored in the various hash buckets. This hash function is better because it takes all the letters in the names into account, but not every such hash function is necessarily good. For example, if we change the 17 in this hash function to a 13, here's the resulting distribution across hash buckets. It's even worse than only counting the first character of each name. This is because the hash tables of size 26 and the multiplier we used was 13, which are related by a simple multiple. To avoid this kind of relationship causing problems, we often choose a table size that is a prime number. Also, it's a good idea for a chaining hash table to keep a load factor of approximately 1. Higher than that, and we need to do more iteration to find the right elements. Lower than that, and we're wasting space that probably isn't required. Here's what our 200 baby name data looks like when slotted into a 211 cell hash table. The other major approach to collision resolution is probing. In this approach, we go back to just one element per cell and add a strategy of looking for alternate cells when we encounter a collision. Since we're now storing all elements directly in the hash table, a load factor of 1 is obviously not a good idea. Less than 0.5 is much better. The simplest probing strategy is linear probing. If we encounter a collision at cell H, we try H plus 1, H plus 2, etc. until we find an empty cell. This strategy is easy to implement, but if we end up with many collisions around a cell or a small range of cells, we may find that we get a clustering effect, in which H plus 1, H plus 2, etc. are already taken, and we have to do quite a lot of work to find an empty cell. Once we do, of course, we make life harder for the next attempt to find a cell for an element that hashes to a similar value. A slight improvement can be found with quadratic probing. As the name implies, after a collision, this strategy looks for empty cells at cell H plus 1, H plus 4, H plus 9, H plus 16, etc. All mod n, of course. It's also possible to apply a second hash function to calculate offsets to alternate cells, but in practice, quadratic hashing does the trick as long as the load factor is less than 0.5. That's a brief introduction to hash tables, hash functions, hash codes, and two forms of collision resolution, chaining and probing. We'll play with these ideas in our in-class exercises. Now that we know what hash tables are, let's dig into some more details about where they're implemented and how they work. We've previously seen that the C++ standard template library type standard map and standard set are typically implemented using search trees, specifically red-black trees, which are a kind of self-balancing BST, kind of like AVL trees. C++11 added the STL types unordered map and unordered set, which are based on hash tables. We can query internal details of the hash table, such as the number of buckets or the current load factor, using public methods that are now part of the standard. Take a moment now to look at a couple of these methods on your favorite C++ reference site and find the answer to our first questions. 1. What is the default maximum load factor for an unordered set? And 2. What can we infer about the internal implementation using this information? As a hash table gets full, its performance degrades because we need to spend extra time dealing with collisions, both on insert, where we need to find somewhere to put the new data, and on lookup, since we may need to do some iteration to find the correct value. In a hash table that uses quadratic probing and that has a load factor over 1/2, we may not even find anywhere to put the new data. As the hash table fills up then, we need to add additional space to it. The trouble is, our hash function maps values to integers in the range 0 through n, not 0 through 2n. If we change the hash function, all of the existing keys or values may map to new places in the table. There's no way around this problem. Whenever we enlarge a hash table, we need to rehash. That is, go through all of the existing entries in the table and calculate new locations for them in the expanded hash table. This is a linear operation. Recalculating one hash code is a constant time operation, but we have lambda n recalculations to perform. If we're going to keep our constant time insertions, we had better not rehash the whole table too often. If we follow the same strategy as vector growth, that is, making sure we double in size every time we grow, then an order n rehash will only happen after adding n entries to the table, so the overall asymptotic performance is still linear. However, it's worth noting that the insertion that puts us over the maximum load factor will be much more expensive than the insertions that precede it. So far we've talked about hash table performance as constant time, but you will likely have observed that it's constant time in the best case, not necessarily the worst case. The average case performance of a hash table operation is also constant time, but clearly it's possible to choose a hash function that, for some pernicious input data, will create lots of collisions and thus lots of work on insertion and lookup. For example, a hash function that, for a given data set, happens to hash all keys to the same hash code will end up having order n operations rather than order 1. This might seem unlikely if we choose a reasonable hash function, but in some spheres unlikely isn't good enough. If you need time guarantees, or if you're worried about an attacker influencing the keys in a hash table, we need to go further. One way to guarantee constant time performance is using a technique called perfect hashing. It is possible to build a so-called perfect hash function if we know all possible keys in advance. Firstly, it can be shown that if we build a large enough hash table, we can have a better than 50% chance that a random distribution of values to hash codes will cause no collisions whatsoever. If we're happy to build such a large hash table, we can generate random hash functions until we find one that has no collisions, and we're done. How can we generate a hash function? By choosing random parameters for the expression ax plus b mod p mod m, where m is the size of the table and p is a prime number larger than m. It can be very efficient to compute the modulus of p if p is a Mersenne prime, which is a prime number that's 1 less than a power of 2. For example, 2 to the 7 minus 1 is a prime number, as is 2 to the 13 minus 1. So, given a value of m, we can choose p to be the next largest Mersenne prime, leaving just a and b for random selection. With a large enough hash table, we should only need to try a few candidate hash functions before we find one that works. However, what is large enough? That's the unfortunate part. We need a hash table of size m equals n squared. That's a pretty big hash table, unworkable in practice. However, perfect hashing isn't quite dead yet. Instead of building a hash table with n squared entries, we can build a regular sized hash table, suffer a few collisions, and, whenever we have a bucket with colliding values, store those values within a second level hash table. Each of these buckets should only have a few entries, so we can afford to make those hash tables quadratic in size. So, our overall strategy is to use one randomly selected hash function for the first level hash table, and then to randomly select hash functions for each second level table, where the size of each second level table gives us a high probability of finding a collision-free hash function within the first couple of tries. This all sounds like a lot of work, but it's not work that we have to do at runtime. It's work that is done at build time. Also, there are tools available to automate parts of the process. See, for example, the open source gperf tool. People are also working on dynamic perfect hashing algorithms that relax the assumption that we know all of the keys in advance, but they're a bit more complicated. I'll leave those as further reading in Chapter 5, if you're interested. So that's a bit about how and where the STL implements hash tables, how and when we rehash the entries in a hash table, and how we can guarantee constant time performance. We'll play a bit with STL hash tables and their rehashing behavior, as well as gperf, in our in-class exercises.